Yay. Okay. I believe we can start like in a couple of seconds, probably in a minute. Okay. Let's start. So what am I going to discuss today? Now I want to switch to the fields. So I want to discuss fields in details. And okay, so what do you want to do? Well, let's discuss some simple basic properties of fields. Suppose we're given a field. F is a field. Then there is such a notion as a characteristic of a field. What is this? Well, let's take the identity element of the field. Then we may start adding one together several times. For example, we may consider 1 plus 1 plus 1, an expression like this, where we add 1 n times. And there are two different options. Well, the option number 1, we will never get 0. The option number 1, for each positive integer, let's say n greater than 0 and n is integer, this expression is never 0. We will not get 0. And the option number 2, there is such a positive integer such that this expression is 0. Okay.
But isn't that just the definition of groups being cyclic and not cyclic?
Well, first of all, I'm not generating a subset. I'm just considering the value of this expression. And what I'm saying is that the result of this expression is either 0 or not. But okay, it's related to cyclic subgroups. And here is how. You may consider F with addition only, so you may forget about multiplication. Then you have this element 1 inside F, and then you may consider its cyclic subgroup with respect to addition inside F. So additive subgroup, additive cyclic subgroup. Yeah, and then the element 1 may have infinite or finite order. So if it has infinite order, this is the option number 1. If it has finite order, then this is option number 2. So yeah, so here if you take a look at the order of 1 inside this group, I mean with respect to addition, because with respect to multiplication, it's not interesting, it's already just 1. Then you have two options. It's either infinite or it's finite. So yeah, and yeah, so this is how it's related to the cyclic subgroup, but I do not generate the whole group because I do not consider -1 and etc.
I'm sorry, can I ask a question? Once again, like, what does it mean that a group of order 1 can either be infinite or non-infinite? Like, doesn't it mean if it has like order 1, it has only one element?
No. The order of an element is a number. So here F is your group with respect to addition. 1 is an element of your group. So this is an element. And this is the order of an element. So what is the order of an element? This is the smallest possible positive degree producing the neutral element. So in additive group, so how do you compute the order? You add the element several times and you consider the smallest possible n such that the result is 0.
Right, thank you.
Yeah, I have a question. Like, maybe it's a little bit stupid, but how is a group and a field different?
Oh, So what is the field? Field is a set with two operations, addition and multiplication. And addition is good, let's say, and multiplication is not very bad. And they are related to each other by some specific law. This is a field. So you have three components, a set and two operations. And what is a group? Group is a set and just one operation. You can denote it by any symbol, just one operation.
Wait, okay, how is a field different from a ring then?
Okay, if you have a field, field is a special case of a ring with additional properties. So in a field, your multiplication must be the best possible, in the sense that it must be commutative and every non-zero element is invertible.
Okay.
So you can divide by any non-zero element inside the field.
Okay, thank you.
Okay. Okay, there was a lot of words here, so let me summarize what's going on here. So I want to formulate the definitions. Suppose F is a field, and consider the element 1, the neutral element with respect to multiplication in F. So then we may consider the order of this element in the additive group of the field. So I consider F with addition, and in this case I may consider the order of the element 1. So and this is a number, or the symbol infinity, and this so this has two options. Either it's a natural number or it's a symbol infinity. So in the first case, so now I want to define the characteristic of a field. I will say that in the first case, if the first case happens, I will say that this number is the characteristic of the field. This is just the order of the element 1 if the order is less than infinity. In the second case, if the order of the element 1 is infinite, I will say that the characteristic is 0. This is just by definition if the order of the element 1 is infinite. So now let me clarify what exactly this means. So how to check what is the characteristic of a field. So first of all, the characteristic is a natural number. It could be 0, but it's a natural number. So how to compute this natural number? You take the element 1 and you consider the expression like this. You add 1 plus 1 plus 1 n times. If you never get the 0 element, the characteristic is 0. And if you get a 0 element, so the characteristic is the smallest possible n, such that this sum gives you 0. So if this expression is not 0 for any n, then the characteristic of a field is 0. And if this expression becomes 0, then the characteristic is the smallest possible n with this property. What is the symbol? Oh, in. The order inside. I mean, in order to be able to talk about an order, I need to specify a group. So this is our group, and I consider this element 1 as an element of this specific group. So, okay, so this was the definition.
May I try and talk about some sort of like analogy? Like, is it like a determinant for a matrix, a characteristic for a field?
No.
No.
Not even close.
So, okay.
I mean, a field is an algebraic structure. A matrix is just an element of an algebraic structure.
Yeah.
So,
okay.
but be patient. You'll see why we need it. But just in case, we have several examples of fields. So let me show you what the characteristic look like there. So an example. Well, if you take Q, the rational numbers, or R, the real numbers, or C, the complex numbers, and you add the element 1 several times, you will never get 0 if n is strictly greater than 0. So the characteristic of all of these fields is 0, just by definition. And we know another example of a field. If we take ZP, the remainders modular prime number, where P is prime, then ZP is a field. This is a field. And this is an example of a field with finite characteristic, because if you add 1 P times, you will get 0, just by the definition of the addition in this field. So these are examples of a characteristic of a field. Okay. What do I want to
just
yep.
What's the name in Russian?
What?
Of characteristic of a field.
Характеристика. In Russian, it's called характеристика.
Okay, just in case.
Yeah, yeah. The term is just a straightforward forward translation from English. So we have no options here. Okay, so let me explain the reason why we define the characteristic in this specific way. I just want to make a remark. So during the seminar sessions, we discussed how to compute all possible homomorphisms from the ring Z of integers to any other ring. So if we consider the ring of integers and an arbitrary field, there is only one homomorphism from Z to F, which takes each integer n to an element n times 1, where 1 is the neutral element of F. So this is the only possible homomorphism from Z to F. And here, F is a field. So, and this is our homomorphism phi. So, okay.
Also, I see the question discarded. Thank you.
Okay, no problem. So now let's take a look at the kernel of this homomorphism. What is this? So the kernel of phi is the set of all integers k such that k times 1 equals 0. Well, and for positive k, this simply means that I want to add the element 1 k times, and I want to get 0. So the kernel consists of all integers k such that k times 1 equals 0. So the smallest possible k, positive k, inside the kernel is the characteristic. And if there is no such positive k, then the 0 is the characteristic. But
I'm
now,
sorry. Can I ask a question?
Yeah.
So is this identity element from F or Z?
It's the identity element from F, because otherwise it doesn't make sense. So let me be more specific. So I want to hear one of F. Okay. Yeah. So this is the identity element of the field F. Otherwise, the result will be on the left-hand side, inside the left-hand side. So now, yeah.
So when we write k times 1 in the field F, we're using multiplication in the field F, right?
Okay, so here I'm abusing the notation. By definition, well, if k is positive, this is just this expression.
Yeah, okay, because I mean, if we were using multiplication in the field F, then it's not the same, I guess.
Well, it doesn't make sense, because how do you multiply integers
k,
with element?
Right?
Yeah, so so this is the definition of this product. And if k is 0, the result is 0 just by definition. If k is positive, it means that you just add 1 k times. And if it's negative, it means that you add module k times the element -1 of f. So this is just the definition of this expression.
No, okay.
Now I hope it's clear what I mean. So this is just for this is just a shortening of this complicated expression when you need to write plus several times. Now the okay.
But
Yep.
like just, I mean, in this case, it makes sense, but in general, I guess it could be a bit confusing because for the field f, we have another multiplication defined. So,
well, you may show that, well, but this is a different multiplication. It's an external multiplication. You multiply by something outside of the
yeah,
field.
I understand, but like in general, it can be a bit confusing.
Well, not really, because you may identify somehow elements n times 1 with the integers, well, up to the kernel. And well, okay, but not really. You'll get used
okay,
to it.
I'll believe you now. Okay.
Yeah, so this is a very common thing people do, but you need to practice a bit and then it's not so confusing. So now my point is the kernel must be an ideal of Z, but we know that every ideal is generated by an integer, let's say p, where p is just a natural number. So this p is the characteristic of f.
Sorry, can you again like make a quick recap of what characteristic is?
Okay, so what is the characteristic? You take the element 1 of your field and you add it several times. If you get 0 when you add its p times, consider the smallest possible p with this property, and then this p, positive p, is your characteristic. And if you will never get 0, your characteristic is 0. So the characteristic shows you how many times you need to add 1 to get the 0 element. Okay, so now what I'm saying that if you consider this the only homomorphism from Z to F, then its kernel is generated by an element P, and this element P is exactly the characteristic of the field. So if you look closely to the definition of the kernel and to the definition of a characteristic, you will see that this number here is exactly the characteristic. But let me skip the details of the explanation. I hope you'll be able to understand it by yourself. Now I want to discuss what kind of numbers will we get as the characteristic. I want to show you that if we have a field, then the characteristic is always a prime number or a 0 number. So a non-zero characteristic must be prime. So let's discuss this. Suppose F is a field. And suppose that the characteristic of F is non-zero. Then P is prime. For example, it's impossible to have a field of characteristic 6 because 6 is not prime. So let me show you how to prove this. Well, suppose the contrary holds, that the characteristic is not a prime number, where m and n are strictly larger than 1. Then this means that if I take 1 and add it p times, I will get 0. But since p is equal to m times n, I can rearrange this sum as follows. Here I have m summons, and here I have n summons. So if you expand this expression on the right, you will have exactly m times n summons, and this is p. So now as you can see, and moreover, since m and n are greater than 1, then they are strictly smaller than p. So since p was the smallest possible number such that 1 plus 1 plus 1 p times is equal to 0, these two expressions are not 0, because otherwise this would contradict to the definition of p. But now this is a non-zero element of a field. So you may multiply this equality by the inverse element. So since this one is not equal to 0, then there exists an inverse element. And after multiplying by the inverse element, you will get 0 is equal to the other element, which is the sum of n elements. And this contradicts, and this is a contradiction, it contradicts to these inequality. I'm sorry for my handwriting, it's awful. So where did this contradiction come from? It came from here. We assumed that p was not prime, and we got a contradiction. So our assumption was wrong, so p must be prime, and we're done here. Okay, so are there any questions, just in case?
Again, just a recap for the people who are thicker in the mind. So if we try to find an inverse of this thing on the left with m summons, we're going to end up with what technically has to be a 0, which is the bracket on the right, which isn't 0, and this is a contradiction.
Yep. So if you cancel by this guy, if you multiply by the inverse of this one, you cancel this factor, and you will. So when you multiply the left-hand side and the right-hand side. If you multiply 0 by anything, you will get 0. And if you multiply,
yeah, that's correct.
Yeah. So you cancel this.
Yeah, now I get it. Now I get it. Thank you.
Okay. Okay, no problem. So now let's move on. Now I want to discuss another thing. So I want to touch a little bit the structure of a field with a prime characteristic. Well, now suppose
actually, wait a second. I have a question about the previous.
Okay.
So, okay, so we have m and n equals 0. Then we say that
not equal to 0.
I mean, m times n has to be equal to 0 because it's p. So then,
well, this is strictly speaking, m times n equals p in z. So this is an equality of integers. So yeah,
like my question is, so we're saying that some inverse is equal to 0. Like I'm not sure where we get the contradiction from.
Okay, so first of all, this is the point where we get the contradiction. We assume that p is not prime. So m and n are strictly smaller than p and strictly larger than 1. So let me add this part here. So m times 1 is not 0, and n times 1 is not 0 because p was the smallest possible integer such that p times 1 equals 0. So, and
yes,
now when and roughly speaking, what we get 0 equals m times 1 times n times 1. So we have 0 divisors in the field. And this is impossible because if we have a non-zero element, we can always divide by this element, which means multiply by the inverse, and the other one must be 0. So it's impossible to have a product of two non-zero elements be 0 in the field.
Okay.
Is it okay, or should I explain something?
Yeah, okay, it's clear, yeah.
Okay, so let's move on, but okay. So now, suppose F is a field, and the characteristic of the field is P, which is not 0. Then the claim is that F contains ZP as a subfield. So every field of a prime characteristic contains the field of remainders modular P, where P is this prime number, which is the characteristic. So let me show you. So first of all, we need to find a subset inside F, which remains ZP. So how would we do that? Well, let's take the element 1 in F, and let's consider the elements 0, 1, 2, etc. Well, it's better to write it like this. 1 of F, 2 times 1 of F, etc. P minus 1 times 1 of F. So this is a subset of F. So you take 0, 1, 1 plus 1, 1 plus 1 plus 1, etc. And here you have exactly P elements. And what is, so this is a subset. I mean, this thing is a subset. And we have ZP. What is ZP? It consists of 0, 1, 2, and so on, P minus 1. And we have two operations, the addition and multiplication modular P. Now, I want to show that this subset can be identified with this field. So then the way how to identify is really clear. There is a bijection between these elements. What I'm saying that this bijection is a well, it's an isomorphism of ZP to a subring inside F. So these guy form a subring, and this identification is an isomorphism between ZP and this subring. So this is the meaning of the phrase that the field F contains ZP as a subfield. So this is exactly a copy of ZP inside F. So now let me be more formal. So we have a map from ZP to F, which takes each remainder K to the element K times 1 of F. It's clear that this map is a bijection between, this map is injective. So this map is injective. So now if we, and let me denote it by phi, the name of this map. Now, if I show you that this map is a homomorphism, so it preserves addition and multiplication, then it will be an isomorphism to the image. So if I show you that it's homomorphism, then the image of phi will be a subring of F, this one exactly, which is isomorphic to ZP, just by the definition of an isomorphism. So I need to check that this map preserves addition and multiplication. But it's clear how to do this. So let me show you. So in order to do, so we need to show that phi of K plus M equals phi of K plus phi of M. We need to show that phi of K times M equals phi of K times phi of M. And we need to show that phi of 1 equals 1. Well, the later one is clear, because just by definition, 1 goes to the element 1. So we need to check these two. Well, first, the way you can check these equalities, is very similar for both equalities. So let me check the first one. So I want to check the first one, and the second one can be done in a similar way. So how do you compute the left-hand side? You first compute the K plus M in ZP. So you consider the sum of integers, and you represent it in a form like this, then R is the result of the sum in ZP. So R is K plus M in ZP. And now you apply the map phi. So phi of K plus M is equal to R times 1 of F. So this is the definition of the left-hand side. So what is the definition of the right-hand side? You just apply phi to K and phi to M. Phi of K just is by definition K times 1 of F, and phi of M is by definition is M times 1 of F. And the right-hand side is K plus K times 1 of F plus M times 1 of F. Okay, so now, and this is phi of K plus phi of M. Now you can present it as a sum of the element 1, K plus M times. And you can rewrite it in the following way. So here you have Q times P elements, and here you have R elements. And by the definition of the characteristic, the first part is equal to 0 because you can divide this sum into Q subsums, and each of them is a sum of P, of 1 P times. So the first sum is 0, and the result is 1 plus 1 plus 1 R times, and this is exactly R times 1 of F. And as you can see, this is exactly this expression. So this is how you check that this map preserves addition. So in a similar way, you can check that it preserves multiplication. So it's similar. And I want to skip the proof of the second part. So this claim shows that each field of a prime characteristic contains ZP as a subfield.
Well, I have a question.
Okay.
How do we know that our phi is injective?
Oh, just by definition, because you see, all elements here are distinct because this is exactly the cyclic subgroup with respect to addition generated by the element 1. All the elements of this of the cyclic subgroups here are distinct.
Again, do we know that one is a generator?
Yeah, because what by definition, what did I do here? I just consider the cyclic subgroup of the element 1 in F plus. So this set is just the cyclic subgroup generated by the element 1 with respect to addition.
Okay, thank you. But it wasn't really clear why 1 plus 1 plus 1 Q by P times is 0.
Oh, these one. You mean these one?
No, like right.
Okay, so let me show you again. So so by the definition of the characteristic, 1 plus 1 plus 1 P times is equal to 0. But what is 1 plus 1 plus 1 P times Q times?
Yeah, but it works in the ZP field. But now we're in F, so it's not a field.
I'm sorry, but all these computation is inside the field F. So this is just an element of the field F. And you have P times Q summons, and you can rearrange this sum in this way, in this form. And this one is 0 just by definition of the characteristic.
Okay, but no, I didn't get it.
Okay, so
okay, we know that order of 1 is P, so that's why
because
by 1 is 0.
Because it's the definition of the characteristic.
Okay.
Yeah, the order of 1 in the additive subgroup.
Okay, thank you.
Okay, now now I want to discuss how to build new fields. So I want to discuss field extensions. So the idea to build new fields is to find a field and then find a bigger field with some properties you want. So now I want to discuss a pair of fields. Well, suppose you have two fields, K and F. And K is a subfield of F, which means it's a field and it's a subring. So these two are fields, and these mean a subfield, which means the inclusion is a homomorphism. Now, in this case, just by definition, you may think of F as a vector space over K. So by definition, F is a vector space over K. Why? Well, what is a vector field? A vector field is a set with two operations. The operation number one is addition, allowing you to add different elements of your vector space. And the operation number two is multiplication, allowing you to multiply each element of a field with each element of your vector space. So here, since F is a field, well, it's a set. It has addition, so you may add elements of F together. And then, since it has multiplication, you can multiply each element of F by each element of F. In particular, you may multiply each element of F by an element of K. So you have the required data to define the vector space, and you may check that all the axioms of the vector space are satisfied here. So F is actually a vector space over K. So, and we denote the dimension of the vector space F over K by this symbol. So this is the dimension of F over K. And it's called the degree of F. Degree of F over K. So this is just a name, a new name for the dimension. And here's an example. If you take K to be R and F to be C, the complex numbers, then you see C is a vector space over R. And you may find a basis of C, which is 1 and I. So this is the basis. And the dimension of C over R is 2. So the degree of C over R is 2. Because this is, by definition, the same number. Okay. Now, suppose we're given a field F, K, and we want to find a larger field. How do we do that? Well, here we can use the ring of remainders from the previous lecture. So suppose K is a field. Consider a polynomial of K of X. Then we may produce the ring of remainders, K of X, quotient by F. Now, an interesting question. So we know that this thing is a ring. It's not necessarily a field, but it's always a ring. So an interesting question is when this ring is a field. So let me formulate the claim. So if we have a polynomial here and K is a field, then the ring of remainders is a field if and only if F is irreducible. So if you want to produce a larger field using this procedure, using this object, you need to take an irreducible polynomial, and then this guy is a field containing K.
So in some sense, f is prime.
Yep. Yep, exactly. So irreducible polynomial is the analogy of a prime number. So it works exactly in the same way as we have for integers.
So that means that our new our new field would contain all polynomials with the root of f, with some root of f by which we divide, if I'm correct.
Yep. You can see the future. I'll be at this point in a minute. So let me prove this claim, and then I will explain what you're talking about now. So, but you're right. That's exactly what I'm going to touch like a couple of minutes later.
Excuse me, before you start, just a question about the example above.
Yep.
You give there a basis of 1 and I, but is I in fact a real number?
Again, is I what?
A real number.
No, I is an imaginary number. It's a complex number with the property I square equals -1. Just by definition, what is the field of complex numbers? C consists of elements of the form A plus BI, where A and B are real, and I is just a symbol for the root of this expression.
Yeah, I know that, but then in the basis, so the basis does not consist of the elements of R.
Yeah, exactly. It cannot consist of elements of R, because otherwise all linear combinations will be inside R. But we want to get the whole C.
How is it related to R then?
Okay, so let me, okay. So I want to write this here. I will correct this part later. So you draw this picture when you deal with the complex numbers. You have the element 1 and you have the element I. So as the real vector space, this is a plane with with two elements, 1 and I, inside its basis. So this is R2 as a vector space. Space over R. Well, because what is by definition, a vector space of dimension 2? It must have a basis consisting of two elements. So the elements 1 and I, they are linearly independent over R. Linearly. And they are generators. So what does it mean that they're linearly independent? A plus BI equals 0, where A and B are real numbers, if and only if A equals B equals 0. We know this property that the complex number is equal to 0 if and only if its real and imaginary part are 0. So this simply means that elements 1 and I are linearly independent over R. Okay. And each complex number has this form, so they generate C as a vector space. Is it okay now, or?
Yeah, it's okay now, thank you.
Okay, no problem. So now I want to discuss how to prove this claim. Okay, so, well, actually, well, let's take f from k of x. Well, if your polynomial is not irreducible, so well, it's not irreducible, then you can decompose it into a product of two polynomials, and the degree of g and h are not non-constant. So g and h are not non-constant. So their degree is strictly smaller than the degree of f. So the degree of g and h strictly smaller than the degree of f and strictly larger than 0. Now, this assumption means that the elements g and h are not 0 in the quotient ring, just by definition, because, well, it consists of all polynomials of degree strictly smaller than f. So these are non-zero elements here. But then, by the definition of multiplication, if you multiply G by H, you will get F, and its remainder modular F is 0. So the result of their product is 0 in this ring. So again, we have 0 divisors, so it cannot be a field. So these guys are 0 divisors. So hence, K of X, wash and F is not a field. This is the case number 1, when F is reducible. Again, suppose the case number 2, F is irreducible. Then the only thing we need to show that each non-zero element of K of X over F is invertible. So we need to take a non-zero element from K of X over F, and we need to show that G is invertible. How do we do that? Well, by definition, the degree of G is strictly smaller than the degree of F, and F is irreducible. Pardon? Is there a question?
Yes, there is one question. In regards to the previous part,
Okay.
you've noted that these two elements that we basically use to get F, multiply to get F, are 0 divisors. How does it make K of X but F not a field?
Okay. If it were a field, then there would be element G inverse and H inverse. And you can multiply by G inverse this equality. Then the left-hand side will give you H, and the right-hand side will give you 0. So if G is invertible, then H must be 0, but H is also non-zero element here, a contradiction.
Oh.
So this is exactly the same argument that I used previously.
Previously, yes, I recall.
Yeah, exactly. Okay.
But that's a contradiction. Why does it make it not a field? Like, isn't it just a contradiction?
No.
Why would it be a field?
It's a contradiction. Well, if we assume that K of X over F is a field, it leads to a contradiction. So it may not be a field. It cannot be a field. If we assume that it's a field, it will lead to a contradiction. So
I see.
So it must be not. It must be something other than field.
I see.
Okay. So now, if we have an irreducible polynomial, I want to show you that this is a field. In order to show that this is a field, I need to check all the axioms. And all the axioms but one are clear. And the only axiom we need to check that each non-zero element is invertible. And now I want to check this. Okay, and so we take a polynomial of degree strictly smaller than F, a non-zero polynomial. And since F is irreducible, then G and F are co-prime. Because their common divisor must be a divisor of F. But we have only two monic divisors of F. It's either 1 or F. But F doesn't divide G because G has smaller degree. So the greatest common divisor must be 1. And
a question in relation to your notation. What does monic stand for?
Oh, it means that the leading coefficient of the polynomial is 1.
Oh,
yeah, because you can multiply by a non-zero element of K, and well, you basically change nothing. So that's why if you want some uniqueness for a greatest common divisor or something like that, you need to specify the leading coefficient. Okay, now, okay, so now F and G are co-prime. So And as we know that when they're coprime, the GCD can be expressed as a linear combination of such expressions where A and B are some polynomials in K of X. And now this equality means that in the ring K of X over F, G times A equals 1. Because how do you compute this product by definition? You multiply A and G as polynomials, and then you take the remainder modular F. And this equality means that the remainder of A times G modular F is 1. Because you can rearrange the sum, you can move this on to the left, and 1 is exactly the remainder. So that, and this equality means that this element is the inverse for the element G. So A is actually G inverse just by definition. So as we can see, each non-zero element is invertible. And the proof is exactly the same as it was for integers. Okay, so now let me explain what we have actually done. So when we have a field K, we consider the ring of polynomials, and we take an irreducible polynomial, and then we produce a new field, which is this, and K, let me denote it by L, and K is a subfield here, because, yeah, we have K inside K of X, and then inside of this quotient field just by definition as a free term. So now this field has a very special property. Let's consider the element X here. Well, in order to avoid confusion, I just want to denote it by alpha, because I don't want to think of X as an element of a polynomial ring K of X. I just want to think of X as an element here in L. So, and I want to denote it by alpha. So by the definition, alpha, well, by the definition of the of this ring, alpha is a root of F in L, because F of X is equal to 0 in K of X over F. That was the definition. If you consider the element F of X, its remainder is 0. So this is the 0 element in K of X over F. So, but since I denoted X by alpha, this means that F of alpha is equal to 0 in L, and this is your L. So not only we can construct a larger field, but we produced a field with a root for a specific polynomial. So now we have the following procedure. If we have a field and we have an irreducible polynomial, we can find a larger field where this irreducible polynomial has a root. For example, this is exactly the way the field C was produced. So what is the field of complex numbers? We started with the field R. We take the polynomial x squared plus 1, which is F, and we consider R of X over x squared plus 1. And this is your C, just by definition, where X is just simply denoted by I. So this is how you produce the field of complex numbers. So this is the generalization of this procedure. You may start with an arbitrary field, and then you take an arbitrary irreducible polynomial, and you can extend your starting field to a larger field where you have a root for your irreducible polynomial. So this is the procedure. And if you want to, so if you have a reducible polynomial, and if you have something like reducible is reducible, then you can decompose it into a product of irreducible polynomials and then you may produce a field where, let's say, P1 has a root, something like L, which is K of X over P1. And then here, the element X, I want to denote it by alpha. This is a root for P1, but since P1 divides F, this is also a root for F. So this is how you produce a larger field with a root for a reducible polynomial. So
excuse me, but if we're talking about a field and that, so the polynomial must be irreducible. How can P1 divide F?
No. Here, F is reducible. So the previous case was about irreducible polynomials. So for irreducible polynomial, you just consider K of X over F, and this is a field. If F is reducible, the quotient is not a field. We already know this. But if you take its prime divisor, irreducible divisor, then and repeat the same procedure for an irreducible divisor of F, then you will get a field, and the element X here will be a root for the initial polynomial F.
Mm-hmm.
So this is how to, So now I want to apply this machinery to study finite fields. Well, in computer science, well, infinite fields are not interesting, but the finite fields, so we want to specify our focus on finite fields because, well, you can store elements of a finite field in the memory of a computer. So let's discuss finite fields. Okay. Let me start with the claim number 1. Suppose F is a finite field. So is a field with finitely many elements. Then the claim number 1, the characteristic of this field must be prime. So a finite field cannot have 0 characteristic. And the second claim, it must contain ZP. Well, the second part immediately follows from the first part. We already know that if our field has prime characteristic, then it contains ZP as a subfield. So we need to show that the first claim holds. But, well, if our field is finite, then, well, this is a finite abelian group. Finite abelian group. And in the finite abelian group, each element has a finite order. So then the order of the element 1 is also finite. But the order is exactly the characteristic of a field, of the field. So we're done. So there is nothing to prove actually. First, so now we have some, well, several pieces of information how our finite field looks like. So first of all, it must have prime characteristic, and it also contains ZP. But we can say even more than that. So let's move on. The next claim, we can compute how many elements a finite field has. Well, so suppose F is a finite field. Of prime characteristic. So we already know that the characteristic must be prime, which is non-zero number, and it contains ZP. Then yeah, since it contains ZP, it's a vector space over ZP. So I want to denote the dimension of F over ZP by N. Well, since F is finite, the dimension is also finite. So that's why it's a well-defined number. But now, what I'm saying is that the amount of elements in F is equal to P to the N. So if we have, let me repeat the claim. So if we have a finite field of characteristic P, then it has P to the N elements, where N coincides with the dimension of F over ZP. So this is the claim. So let me explain why this is true. Well, okay. Well, F, we may consider F as a vector space over ZP. Well, since F is finite, well, there are finitely many elements in F. So each basis has has finitely many elements. So each basis is finite. Hence, the dimension of F over ZP, which is N, must be finite. So this is just an explanation why this number is finite. But if we have a finite dimensional vector space, well, let's take its basis. Suppose that E1, En in F is a basis. What does it mean? It means that each element X of F has a unique representation in this form. So this is just a definition of the fact that E1, En is a basis over ZP. It means that each element X is uniquely represented in this form. This simply means that it has as many elements in F, as many expressions of this form we have. But how many expressions of this form we have? We have P options here and P options here. So for each coefficient, we have P options. Why? Because these coefficients from ZP. So we have P times P times P and so on, options for the element X. So we have P to the N options here. So P to the N is the amount of elements of F. And we're done. Well, roughly speaking, what we're doing here, if the dimension of F over ZP is N, then F as a vector space is isomorphic to ZP to the N. So this is what was going on here. So if you prefer, well, a more general proof, like using some fancy words, then what we did here is this. We said that if we have a finite dimensional vector space over field ZP, then it's isomorphic to ZP to the N, and ZP to the N has P to the N elements, so that's why this is true. So, for example, it's impossible to have a finite field with 6 elements, because the amount of elements in a finite field must be a power of a prime number. Okay, now let's discuss another property, which is very important for cryptography, but I believe I want to switch to a different column.
Excuse me, may I ask a question?
Yeah, no problem.
In the previous claim, in the proof, you had this strange notation. Looks like a word fag.
Oh, finite abelian group.
Oh, okay. I forgot that it can be shortened like this. Thank you.
No problem. Yeah, there are a lot of funny words.
No, it's not funny. I just didn't understand what it meant.
Okay, no problem.
I mean, especially if you're a British person, it's not that funny.
Okay. Okay, so let's move on. Now, the next claim, I want to discuss the structure of F star of a finite group, so of a finite field. Suppose F is a finite field. And what I'm saying that F star is cyclic. Saying F star, I mean all invertible elements, which means all non-zero elements of F with respect to multiplication. So let me specify that the operation here is multiplication. So F star with multiplication is a cyclic group. So you may find a generator for this group. So every non-zero element of F is the power of a special element of F. So this is what it means, that you can find an element such that each non-zero element of F is the power of this special element. Okay.
Is the power in relation to what?
Oh, to multiplication.
There are two up.
Multiplication. When I discuss F star, I'm talking about multiplication. When I discuss F, well, then this is not a group, this is a field. So yeah, here I mean multiplication. So, okay, let me show you how to prove this. Well, first of all, this is a finite abelian group. Why? Because it's an abelian group, because multiplication is commutative, and it's finite because you have one element less than in a finite field. But for finite abelian groups, we know that this group is isomorphic to a direct product of cyclic groups, such that D1 divides D2, etc., divides dk. So we know this is the structure theorem for finite abelian groups. What does it mean? It means that dk, so the order of each element here, so it means that for each element h here, the order of h divides dk. Because you see, well, if you raise, well, here you have, so on the right-hand side, the operation is addition. On the left-hand side, the operation is multiplication. So raising to a power k here is multiplying into the number k, to the number k here. If you multiply here each element by dk, you will get 0. So if you raise each element here to the power dk, you will get the neutral element 1. So because of this isomorphism, we see that h to the power of dk is equal to 1. So let me repeat what's going on here. So we consider F star with multiplication. Since it's finite abelian group, we know that its structure must be something like this. And using this isomorphism, we see that each element here, which is h small, if we raise this element to the power dk, we will get the neutral element 1 of this group. So this is the power of an isomorphism. So this simply means that each element of F star is a root of the polynomial x to the dk minus 1. But each root is a linear factor of a polynomial. And because of the UFD property, each polynomial may have at most its degree, well, the amount of linear factors is not larger than its degree. So, I mean, since h is a root, it means that x minus h divides x to the dk minus 1. So each element of F star gives you a linear divisor, linear polynomial dividing this one. But you have at most dk linear factors. So you have at most dk roots. So this simply means that f star, the amount of element in f star, is not greater than dk. From the other hand, since we know that f star is isomorphic to this group, it has exactly the same amount of elements as the right-hand side has. But how many elements on the right-hand side? It's a product. So as you can see, from one hand side, this number is not greater than dk. From the other hand side, this number is equal to d1 dk. And we know that d1 divides d2, etc., divides dk. So how is this possible? When you cancel dk, you'll see that d1 times d2 times dk minus 1 is not greater than 1. So the only option for this is when d1 must be, and d1 is greater than 1. So the only option here is that you have only one factor here in this expression, because if you have at least two factors here, this product will be strictly larger than dk. So from this, it follows that f is actually isomorphic to zd with one factor. And this means that this thing is cyclic. And we're done. So this is how you prove this. Whew. Okay. Just in case, are there any questions regarding the proof? Is there anyone who thinks that he understood the proof?
Could you please repeat the last step?
Yeah, the last step.
Oh, the last step. Okay, so let me overview the proof. So we have this isomorphism of abelian groups. On the left-hand side, we have multiplication. On the right-hand side, we have addition. Now I want to compute elements of f star using two different procedures. First of all, since this is an isomorphism, f star has exactly the same amount of elements as here. So this is the product. From the other hand, here, we estimated the amount of elements by the number dk. So we have like d1 times dk is not larger than dk. And by the way, we also know that all these numbers are arranged in the following form. d1 divides d2 divides etc. divides dk, and d1 is strictly larger than 1. So this is the part of this structure theorem. So I didn't mention it here, but this is the part of the theorem. All these numbers must be greater than 1. So if k is greater than 1, so if we have at least two numbers, so we have dk and something else, then this product must be larger than dk. So this equality cannot happen if k is more than 1. So from this inequality, it follows that k must be 1. So we have only one factor here. So f star is isomorphic to z d1, and that's it. Is it clear now?
No.
Okay. Again?
No, it's not clear.
Which part is unclear?
What is decay?
What is what?
Decay.
Oh, decay. Okay.
It's the last divisor?
Yeah, it's this number for the last factor.
Okay. What do we have only one factor?
Why do we have only one factor?
No, I mean, it's possible. There is a situation when we have only one factor, only dk, only d1, when k is equal to 1.
It's possible that we have only one factor if we have a cyclic group, and we want to show that we have only one factor. We want to show that there is only one factor that, it's impossible to have several factors.
Okay, could you repeat this part, the last part? Again?
Okay, so the last part is this. Because of some ideas here, we have this inequality. Let me underline the inequality. dk is not smaller than the product of d1 dk. And we also have this property that d1 is larger than 1. it divides D2, D2 divides D3, etc. That was the part of the classification theorem for the finite abelian groups. So now we have this blue and red property.
Yeah, okay. I mean, yeah, now it's clear, but how do we know that decay is greater
than 1?
No, greater than dimension of F star.
Oh, that was this part.
Our previous theorem, right?
No, it was this part. So here is the proof that F star, the amount of elements in F star is not greater than decay. So because of this isomorphism, we proved this. H2 decay is equal to 1.
Okay. And
this means that H is a root, so each element of F star is the root of this polynomial. But each polynomial has at most its degree of roots. So since the degree of this guy is decay, you have at most decay roots.
Okay.
So this is the crucial part. So this is how you do this, because in a field you cannot have more than the degree of a polynomial amount of roots.
And why order of H divides decay?
Oh, so well, this part is important. This one was just an attempt to explain the later one, but it's more important to explain this one because I use this. So why? Well, you see, what does it mean that you raise an element to the power of d here? Well, here operation is a multiplication, and here operation is addition. So raising to the power here means multiplying by this power here. Okay.
Okay.
So if you how to prove this? You need to prove that each element here to the power of d is 1. This is the same as to prove that each element here multiplied by d is 0. So if you take decay, if you multiply everything here by decay, so since d1 divides decay, after multiplying the first coordinate by decay, you will get 0, because the result will be divisible by d1 and it will be 0. In the second coordinate, you have zd2, and d2 also divides decay. Then multiplying by decay, you will get 0, etc. So in all coordinates, if you multiply by decay, you will get 0. So this is how this group works. So now we see that on the right-hand side, if you multiply by decay, you will get 0. If you translate this to the left-hand side, this means that if you erase each element to the decay, you will get the neutral element, which is 1. Is it clear now, or?
Especially this part is not clear. Why do you multiply something by decay?
Again, okay, so under this isomorphism, if you take H to D, these, well, let's say it's phi, when you go from the left to the right, then, well, if you element, okay, let's write this here below. If you have a map from F star to the product of, to this product, which takes H to some sequence like A1, etc., AK, okay? Then where does H times H goes? It goes to A1, etc., AK plus A1, etc., AK. So H squared goes to 2A1, etc., to AK.
Okay.
So if you take H to the D, it goes to dA1, etc., dAk.
Okay.
So now, where does the neutral element 1 goes? It goes to the element 0, 0, 0, because the neutral element must go to the neutral element.
Okay.
So if you want to show this equality, it's exactly the same to show this equality.
Okay.
So now if I can show you that each element here.
Okay, yeah, and there's a set of reminders.
Yep.
Okay.
Yep, exactly. Is it clear
Okay,
now?
yeah, yeah.
Okay, no problem. So let's move on. Yeah, and I see that well, my time is over, but I have to explain several things. Well, so I have to proceed. So if you have time, then stay with me. If you don't, then you can see these as a record, as a recording. Okay, so now I want to formulate another claim without proof. And so now what do we know actually? We know something about the structure of finite field. We know that it has finite characteristic, it has prime characteristic P, it contains ZP, and it has P to the n elements. And we know that its group of non-zero elements with respect to multiplication is cyclic. But we know even more, that if we fix a prime number and we fix any positive integer, then there exists unique finite field such that it has P to the n element. So we know that each finite field may have only P to the n elements, and for each option, for each case P to the n, we have only one field with this amount of elements. This is a hard result. So this is not something we can prove like in a second. But we can, so this simply means that we can produce a field with these many elements. And the field with this amount of elements is unique up to isomorphism. So if we have two fields with P to the n elements, they are isomorphic. So it's an interesting question is how to produce such a field. So let me show you the idea of how to produce such a field. First of all, a remark. The remark number one, well, if n is equal to 1, which is P to the 1 amount of elements, in this case, we have ZP. Oh, yeah, and by the way, I forgot to mention the notation. Since we have only one specific field for this amount of elements, we will denote this field as Fp to the n. So this will be the notation for this unique field with P to the n elements. So simply, well, now using this notation, we see that Fp is the same thing as Zp. So if we have, if we want to produce a field with P elements, we just take Zp, and this is just a new name for this guy. So if you see this name, don't be foolish, but it's just Zp. But if you want to produce a larger field, you cannot take Zp to the n. So just a clarification that these two guys are not the same. Why? Because, for example, here you have nilpotence. For example, P is not 0 in this ring, but P to the n is 0. But field cannot have nilpotent elements. So the structure of this guy is more complicated than just the ring of remainders of an integer. And here, what we can do, we can take an irreducible polynomial in Zp, let's say of degree n. So we need to know how to produce an irreducible polynomial of degree n, and then we may produce this field, and this field will be Fp to the n. So, well, why? Because, well, we know how to compute the amount of elements here. So this thing is an n-dimensional vector space over Zp. So that's why it has P to the n elements. And one additional remark, we have many, we may have many irreducible polynomials of the fixed degree n. So we may use different polynomials here, but all these fields will be isomorphic. So it doesn't matter which which polynomial f you use here. If it's irreducible and its degree n, this procedure gives you a finite field of this size. So this is how it works. So I'm not going to specify. Well, I'm not going to go into details how to produce it. So I just skip the example and leave it for the seminar. But now I want to discuss some applications of this thing. I want to discuss the Galois random generator and stream ciphers. So I'll try to be quick. So applications. I just don't want to leave it for the next lecture. So if you allow me. So the Galois random generator. So what is this? Well, let's take ZP as an alphabet. So this is our alphabet. And we want to produce random sequences of this form. So we want to produce these sequences randomly. How do we do this? Well, first of all,
excuse me, but what constitutes randomness?
Okay, so let me explain. We want a procedure, a sequential procedure, which, well, a function. Let's say we want to write an algorithm for a function, and this function will work like this. It returns you an element of this form. And when you call this function several times, well, it returns you, well, some probably different elements of this form. And this sequence look like a sequence that produced by random variable uniformly distributed on the set of these sequences. I don't want to go into details what it means exactly, that it looks like a sequence generated by a random variable. I don't know, probably you will have a course in random variables in probability theory the next year, so you will see all the details. But now, well, let's assume that, well, we don't know what this exactly should mean, but we know, like, philosophically, like our intuition may should work here. So you want some procedure which gives you something which reminds like randomly generated sequence in some sense. I hope this explanation is enough. I don't know. Is it okay if I pronounce the word like this?
I mean, I for one would probably not get it if you did it any more complex at this point. So I guess so. Has to be.
Yeah, but don't worry. I don't want to explain precisely what it means that we have like randomly generated sequence. So you'll see. Well, the sequence, so we want to produce a sequence of elements such that it satisfies several properties and it looks like something random. But I don't want to be more precise with the details. So let me show you the construction. So what I'm going to do. So first of all, to deal with these sequences, you see this is the set ZP to the n. So instead of dealing with ZP to the n, I switch this to FP to the n, and I produce this set as this quotient ring where the degree of f is n. Then, well, how do I identify these sequences with elements of this field? Well, I know by definition that all elements here are of this form,
Excuse me, may I ask a question?
Yep.
I'm just getting confused in definitions. So Z p to the power of n is a field, right?
No, well, here I have no structure for field. It's just a set of sequences.
Oh, so it's just a set, so it shouldn't be a field.
Yeah. So it's just a set. So this one is a set.
Okay, then my question gets discarded. Thank you.
Okay, but now it's inconvenient to deal with a set. I just want to provide more structure on this set. I want to make the set to be a field. So what does it mean? Well, it means that I just find good operations on this set such that, well, I have some good combinatorial properties for these operations. So, but strictly speaking, what I'm doing, I just consider this field. I produce this field using this construction. Then each element of this field is of this form, and it has n coefficients, and its coefficients by definition are from ZP. So its coefficients give me this sequence of length n. So now if I want to take an element from here, it's the same as to take a sequence from here. So now what I want to do, I know that Fpn star is cyclic.
Excuse me, that should be plus a n minus 1 x to the power n minus 1.
Oh, yeah. Thank you very much. Yeah, n minus 1. So now the multiplicative group of this field is cyclic, so it's generated by some special polynomial g. So we may take this polynomial g, so g, where g is from here. What does it mean? It means that each non-zero element of Fpn is the power of g. So now we need to find this one. And it may happen that the element x is a generator. But it may happen that x is not a generator, but we need to take something else. But we need to find this element only once. And then we take an arbitrary polynomial here. And then we may produce a sequence like this: h times g, h times g squared, h times g cubed, etc. And we may take a look at the coefficients of this sequence. Then we take the coefficients. So and this is the sequence I wanted to produce. So, well, this will be a sequence of elements which looks like a random sequence, uniformly distributed among all the non-zero sequences. Well, there are some strict results saying that this sequence satisfies some specific properties, but from the practical point of view, what is important is this: if you want to produce some sequence of elements which look like you generate something randomly, this is one of the ways you can do. So this is one of the ways how you can do this. So this is your sequence, like random sequence. And the procedure that gives you this sequence is called the Galois random generator. And there is one final remark: since H is also in the cyclic subgroup generated by G, this guy is actually G to the K0. So we actually take the powers of the element G, but starting from some fixed power K0 plus 1. So instead of choosing H, we could choose a starting power for G, and then just cycle through all the powers. So we just get G to the power of K1, G to the power of K1 plus 1, G to the power of K1 plus 2, and so on. And then compute the coefficients, and the coefficients will give you this sequence. Okay, so this is the Galar random generator. And here is the application of a random generator. It's called stream cipher. Stream cipher. So now I want to be in a very simple situation. Let's take Z2, which contains 0 and 1. We may take a different approach, but let's say we take the alphabet containing only 2 elements. And now you want to send a message of bits to someone, but you want to encrypt this message. What you can do, you can randomly generate a sequence of other bits, S0, S1, S2, S3, and instead of sending the initial sequence, you add these 2 bits together, and you will get the decrypted information, encrypted information. Encryption, I always forget which word means what. And then you send this information instead. And how to recover the information? You need to know this sequence on the right-hand side. So if you know this sequence, you can recover the initial bits, A0, A1, A2, and so on. So in order to do that, you need a method to generate this sequence for the one who sent the message and for the one who received the message. So let me show you how this is done. So what you have some kind of random generator. You need to have 2 different random generators, and they must be synchronized. And then you have, you have a block which adds bits together, and you send kth bit here. This guy sends you kth random number. Then you send the result to the other person. And here, exactly the same random generator synchronized with your one generates exactly the same symbol sk, and it adds it to the bit that came here, which is dk, and you extract the required bit ak. But in order this thing to work, you need these 2 synchronized random generators, and you may use something like the Galar random generator to do that. Well, this is just a basic scheme how to do this. And the reason, well, this scheme need not be very secure. So you need to get the alphabet, the random generator, the function here to be very specific in order this to be secure. But the modern standards of GSM uses the ideas of this form in order to encrypt and decrypt your data. For example, format like A5 and all its sub-modifications. Okay, so this is how to apply a random generator for stream ciphers. Yeah, and the reason why it's called stream cipher, because you have a stream of data here, and you encrypt and decrypt each piece of information with a new specific element, and these specific elements must be synchronously generated on both sides of your connection. And this is it, and that's all that I wanted to tell you today. Are there any questions?
Can I ask like a derailed question about cryptography altogether?
Okay.
So, like at the very basis of our encryption and decryption is some sort of cyclic group, which has a generator G, which we raise to the powers A and B, which gives us the private key.
Okay.
So the private key is merely private because the generator G is unknown. But how do we transmit generator G through an insecure channel?
Oh, do you mean here?
No, like referring to one of your previous lectures.
Oh, but no,
And
G is not a
it
secret.
And
G is not a secret. The generator G is not a secret.
Wait,
Everyone knows it.
But then, if G is raised to the power A and then to the power B to get the private key, and A and B are public keys. If I understand everything
not
correctly.
A and B. G to the A and G to the B are public keys.
Oh.
A and B are hidden.
Oh yeah, because.
Yeah, that's the point. You cannot recover A and B in this procedure.
I see. Because you have to find the logarithm, and that sucks.
Yeah, exactly.
Oh, I see. I misunderstood this one. I misunderstood that you sent G to power A and G to power B, respectively.
Yeah, exactly.
I see.
And here, the way how this thing works, you usually have two channels: a secure channel, a red channel, and insecure channel. And it's very cheap to send data here, and it's very expensive to send data here because you have a lot of computational work to do. And usually, why do you need this? Well, if you want your connection to be fast, you want to transfer all the data here. So what you do at the beginning of your communication, you use a secure channel. What again?
Второй.
Kirill?
Wait, sorry.
Okay, so what you're doing here, you use your secure channel to synchronize random generators. So you do it at the beginning, and it's not very cheap, but you do it only once. And then when the random generators are synchronized using this encryption, the algorithms from the previous lectures, then you can use this simpler version to transfer all the data here much faster, because this block does its job very, very quick. Very, very, very quickly. So somehow you can combine all the ideas here in order to make a very secure and stable approach.
And I guess it's not even the bottom of the rabbit hole yet.
Yeah, exactly.
Maybe not even the middle.
Exactly. And even here, I didn't cover all the subtleties of how all these blocks work. Yeah. But I just wanted you to know all the basic ideas. And yeah, let me write this down. GSM says hello to you here. Yeah, and usually you switch your random generator after several, after a specific amount of bits sent. This is how GSM works. It bursts several packages, and then it resynchronizes the random generator, and then it again sends several packages, and then it resynchronizes a random generator, and so on and so on. And everything is done on the level of a hardware. So yeah, it's very quick.
And I mean, it has to compensate for many things also, like in the practical world, I guess. Well, in the real world, I mean.
Probably. Okay, but I believe, okay, so are there any other questions?
Yeah, I have a question. Actually.
But you have like 6 minutes.
Oh, okay, I'm okay with it. So we have a theorem which says, I don't know, that our field has p to the power something, no, g to the power p elements.
P to the power of n elements. Okay, this one.
What is p in this case?
Okay, p is the characteristic. So we take a finite field, and we know already that this finite field has prime characteristic p.
Okay, and what is n?
And n is the we know that if it's finite field, it contains ZP. So you may consider your field F as a vector space over ZP. So n is the dimension of F over ZP.
Okay, yeah, and my question is, as I remember, field is a ring. It's a ring, right?
Yep.
And the ring is a group.
Well, a ring is a field with two operations, addition and multiplication. And with respect to addition, the ring, the set of the ring, with respect to addition is an abelian group. But the set of your ring with respect to multiplication is not a group, because your elements are not necessarily invertible with respect to multiplication. And the zero element is almost never invertible with respect to multiplication. So with respect to one operation, it's an abelian group, and with respect to other operation, it's not a group.
What?
Well, again, what is a ring? A ring is a set with two operations. So
Yeah.
if you have a ring, it's a set with two operations. What is a group? It's a set with one operation. So when you say that you have a ring and you want to consider it as a group, you need to specify which operation you mean. So you have two options. You may consider R with addition, or you may consider R with multiplication. And when you consider R with addition, it's an abelian group.
Okay.
Because of the axioms. And if you consider R with multiplication, it is not a group. So this one is not a group, and this one is the best possible group, which is an abelian group.
Okay, and what is characteristic by the definition?
Oh, by the definition, well, you take a field, you forget multiplication. So now you
and characteristic is the smallest number.
Yeah, and you take the order of the element 1.
Okay, but I claim that.
Yeah.
Okay, I claim that my set, my group, might have more than one generator.
I'm not saying that this is not a question about the generator. You have this specific element 1, where 1 is the neutral element with respect to multiplication. There must be one neutral element in the field. So it's 1 is prescribed element. So inside F, you have only one element with the name 1. And you want to compute its order, not an arbitrary element generated something somewhere in some sense, but you take this specific element 1.
Okay, yeah, now I see.
And for this specific element 1, you compute its order.
Okay, we take this order as a characteristic. It's p, and p to the power n is the number of elements.
Again?
Like, I mean, we take this order 1, we denote this as a characteristic as p, and the number of elements is equal to
p to the n.
P to the n, okay. Okay, thank you.
But here, the relation you need to know that if the characteristic is p, then your field contains zp as a subfield. So the reason why you have this is because inside your field you have zp, and zp has p elements.
Okay, good. Yeah.
So this is the crucial part.
Okay, could you go through this claim again, please?
This one?
This one? No, previous.
The previous one.
Yeah.
Okay, but yeah, I'm just derived this claim from all the things we had before. So if we have a finite field, then, well, F is finite. So F with addition is a finite abelian group. But in a finite abelian group, each element has finite order. So the characteristic is finite. And we know that if our characteristic is finite, then it's prime. So this is the first part.
Okay.
And the second part, we have already shown that if the characteristic is prime, then ZP is inside F. That was somewhere here. I don't remember. Probably no. Probably it was somewhere before.
It has been so long.
Yeah, it's. I don't know where was that.
And now with plus, it's a finite abelian group, but just because of definition, right?
Yeah, because F plus is an abelian group by definition. The axiom for the addition says that F with addition must be abelian group.
Okay, so we have the finite set, which means that it's a finite abelian group. Order of one. Yeah, order for every element is less than infinite.
Oh yeah, by the way, we need to switch to the seminar because literally the seminar is starting right now. We have to stop this stream and switch to the seminar. Let's discuss it later, okay?
Okay.
Okay, guys, thanks for being here. I hope that was interesting. See you the next time.